Rotary drilling requires some type of drilling fluid. As the bit makes cuttings, drilling fluid is needed to lift the cuttings, carry the cuttings up the hole, and to the surface for disposal. As seen in the pits, drilling fluid is usually a liquid and is called mud. But not all drilling fluids are liquid. Note the dust in the background at left. The dust shows that air or gas is being used as a drilling fluid on this rig. Here, a drilling fluid that is a combination of liquid and gas, mist, is coming out a rig's bluey line. Other gaseous mixtures include foam and aerated muds. So there are three basic classes of drilling fluids: water base and oil muds, both of which are liquid like the mud here, and gaseous fluids like air, gas, mist, foam, and aerated muds. Since most rotary drilling fluids are water-based muds, let's concentrate on them. Water-based muds consist of three parts, or phases, as mud engineers like to say. First is the water phase. Second is the active solids. And third is the inactive or inert solids. What do we mean by active and inert? Well, by active, we mean that the solids respond or react when they contact chemicals. Here, for example, bentonite clay, an active solid, has been put in a beaker of water, which is a chemical, by the way. The bentonite has reacted with the water to form a thick, viscous liquid. Bentonite also reacts with other chemicals. By inert, we mean that the solids do not react with chemicals. Here, barite, an inert solid, only settles to bottom and does not react. Nor does barite react with the other chemicals. When the active clay solids and the inert solids are mixed into water, a basic water-based mud is formed. Mud is a special fluid called a suspension that has all sorts of interesting properties. For example, since drilling mud is a suspension, the active and inert solids are spread out in the water and do not settle out even when the mud is not moving. Do not confuse a suspension with a solution. To show you a solution, table salt is being added to water and stirred until all the salt dissolves in the water. When the salt solution is poured through a funnel that has filter paper in it, a look at the filter paper shows that no salt was filtered out. There is no salt on the paper. The salt is still dissolved in the water. But look at this filter paper. The tan material is solids that have been filtered out of drilling mud. So in a suspension, the solids are not dissolved in the liquid, are larger, and can be filtered out. But in solution, the solids are dissolved and cannot be filtered out. Another interesting property of drilling mud is that it is denser or has more weight than water. By just adding clay to the water, we increase the weight. In fact, clay is about 2.5 times as heavy as the same volume of water. Also, viscosity or resistance to flow increases when active clay solids are added to water. The viscous liquid is able to carry cuttings from the hole and support barite. In addition, gel strength is obtained. That is, as at left, when the mud is not flowing, such as when a connection is being made, it temporarily solidifies or gels and keeps large cuttings from falling. but as at right, when the mud is pumped, it thins and is able to flow. Finally, filtration control is obtained when active solids are added to water. By filtration control, we mean that loss of water from the mud to a permeable formation is decreased. The solids form a cake on the walls of the hole and keep most of the water, or filtrate, from getting into the formation. To summarize what we've seen so far, there are three basic classes of drilling fluids: water-based muds, oil muds, and gaseous fluids like air, gas, and mist. A water-based mud consists of three parts, or phases: water, active solids like bentonite, and inert solids like barite. Active solids react with water to form a suspension. The active solids build viscosity, add weight, and give the mud gel strength and filtration control properties. If workbooks are available, stop cassette and work Exercise 1. As we watch a derrick man adding water to mud, let's talk in detail about the water phase. The kind of water affects the way the active solids react. So water affects the viscosity, gel strength, and filtration properties of the mud. Fresh water, like the water we drink, is often used in a mud. It contains little, if any, salt, and little or no substances like calcium or magnesium. Fresh water weighs about 8.33 pounds per gallon, 62.4 pounds per cubic foot, or 1 kilogram per liter. Another water used in muds is hard water. Hard water contains calcium, Ca, and magnesium, Mg, in solution. Hard water weighs about the same as fresh water, 8.33 pounds per gallon, 62.4 pounds per cubic foot, or 1 kilogram per liter. Incidentally, hard water can be softened by adding chemicals like soda ash, phosphate, or caustic soda. On offshore rigs, seawater is used to make up mud. Seawater weighs about 8.56 pounds per gallon, 64 pounds per cubic foot, or 1.03 kilograms per liter, and contains many substances in solution, like sodium, chlorine, magnesium, potassium, and sulfates. Salt water made with sodium chloride, NaCl, is another type of makeup and treating water. The amount of salt dissolved in the water may be as high as 260,000 parts per million. With this much salt, the solution is saturated at room temperature, which means that no more salt can be dissolved in the water at that temperature. Saturated salt water weighs about 10 pounds per gallon, 74.8 pounds per cubic foot, or 1.2 kilograms per liter. How many times have you seen bentonite clay or gel being added to the mud? Well, you may not have known it, but gel is made up of active solids, solids that react with water to give viscosity, gel strength, and fluid loss control. Of course, there are other active solids besides bentonite or gel in the mud. For instance, some of the clays and shales drilled are active. They enter the mud and become part of the mud system unless they are large enough to be removed at the surface. To see how active solids behave in water, look at a highly magnified single particle of bentonite clay. The particle is flat and plate-like and consists of three layers: two outside layers of a substance called silica and a central layer of alumina. The whole particle is negatively charged. This clay particle acts much like the negative end of a magnet. The particle attracts anything with a positive charge. One thing with a positive charge is a cation. The particle draws the cations to the silica surface layers. The cations drawn to the clay particle may, as at left, be sodium, abbreviated Na, or as at right, calcium, abbreviated Ca. If the cations are predominantly or mostly sodium, then the clay is known as sodium clay. If the cations are predominantly or mostly calcium, then the clay is known as calcium clay. The particles of clay are stacked up one on top of the other like a deck of cards. Each card represents a clay particle consisting of 3 layers with the cations located on or near the card face. When the clay particles are added to water, the particles separate. Each then becomes surrounded by an envelope of water. If the clay is sodium clay, each platelet has a large envelope of water around it. But if the clay is calcium clay, then the water envelope around each platelet is smaller. Calcium clay does not take on or absorb as much water as sodium clay. So it takes more calcium clay than sodium clay to build the same viscosity, about 4 times as much. Here's what we actually see. At left is a piece of sodium clay, crude bentonite. The beaker at right shows what happens when the clay is put in water. The clay hydrates. It takes on, or absorbs, so much water it expands to about 8 times its original size. This means that viscosity is very high. On the other hand, if the clay is calcium clay, calcium montmorillonite, hydration is not as great. Calcium clay only swells about 2 or 3 times its original size. Therefore, calcium clay does not give as much viscosity as sodium clay. This is a particle of bentonite or sodium clay taken through a microscope and enlarged 35,000 times. It is flat, platy, and looks kind of like a fanned-out deck of cards. It is this flatness, plus the particle's extremely small size, that makes bentonite good for filtration control. The flat bentonite particles, as enlarged in the circle, build up on the wall of the borehole, much like shingles on a roof, and prevent the water phase of the mud from escaping into the formation. Calcium clay does not have the same ability to control filtration. Its structure and size are different from sodium bentonite. Another fact is that sodium clay, or bentonite, reacts differently when put in fresh water and in salt water. After 72 hours, the piece of bentonite in the fresh water hydrates and swells as expected, but the piece in the salt water hasn't hydrated very much. Mud engineers call this inhibition. That is, salt water retards or inhibits bentonite's ability to hydrate. As a result, the viscosity of the bentonite and saltwater suspension is considerably less than the bentonite and freshwater suspension. Thus, freshwater clays, like bentonite, are not added directly to saltwater to build viscosity. However, bentonite can be used to obtain viscosity in saltwater. Here, powdered bentonite is being added to fresh water and allowed to hydrate. Then the prehydrated bentonite freshwater slurry is added to salt water and viscosity is obtained. So if necessary, viscosity can be built in salt water with freshwater clay by prehydrating the clay in fresh water. Calcium in water also inhibits the hydration of bentonite. In the beaker at left, calcium chloride is dissolved in water, and in the beaker at right, calcium sulfate, or JIP, is dissolved in water. With a piece of bentonite in a beaker that has calcium dissolved in it, and after a 36-hour wait, the bentonite has not hydrated very much. The fact that calcium inhibits the hydration of bentonite is sometimes used to advantage. Like when shale is being drilled, that contains various types of clays. It's not good for these drilled solids to hydrate because they have bad effects on borehole stability and mud properties. Calcium-treated muds keep the solids from hydrating too much. If you've been on rigs where saltwater muds are used, you've probably seen saltwater clay or attapulgite. Attapulgite is used to build viscosity, since bentonite doesn't hydrate very much in salt water. Interestingly, attapulgite doesn't hydrate in salt water either. The attapulgite in this beaker of salt water has just settled to bottom without hydrating. So how then does attapulgite build viscosity? Well, the answer is that attapulgite builds viscosity by a shearing action. The attapulgite particles must be stirred vigorously into the salt water so that the particles will stick together and form a structure like a brush heap or haystack. A photo through a microscope shows attapulgite's needle-like shape. Because of its shape, attapulgite doesn't provide much filtration control. There are no nice flat particles to stack up on the wall of the hole. So in attapulgite muds, fluid loss is controlled by adding starch, as is being done here, or cellulose to the mud system. Now let's talk about inert solids. Inert means that the solids are chemically inactive. They do not hydrate or respond to chemical treatment. The barite added here has settled out because of this. The most commonly used inert solid is barite, like the derrick man is adding here. It is used to weight up or increase the density of muds. Sometimes calcium carbonate or iron carbonate is used. Drilled inert solids are also in the mud. As the bit penetrates sandstone, dolomite, and limestone, the solids become part of the mud. But primarily, we're interested in barite. Barite is heavy. A gallon of water weighs about 8.3 pounds, but a gallon of barite weighs about 35 pounds. That's 4.2 times as heavy as water. If you're used to pounds per cubic foot, a cubic foot of water weighs about 62.4 pounds, and a cubic foot of barite weighs 262 pounds. And since it looks like we're all going to have to get used to the metric system, a liter of water weighs 1 kilogram, and a liter of barite weighs 4.2 kilograms. But no matter how you weigh it, barite is heavy, and for that reason is used to weight up muds. In fact, we can get muds that weigh up to 22 pounds per gallon, 165 pounds per cubic foot, or 2.63 kilograms per liter. To summarize this section, first we talked about the water phase of water-based mud and saw that freshwater, hard water, seawater, and saltwater are used to make mud. Then we discussed active solids and saw that bentonite swells or hydrates in fresh water to build viscosity, gel strength, and filtration control properties. Also, sodium clays, bentonite, hydrate more than calcium clays, calcium montmorillonite, and sodium clays do not hydrate very much in salt water. Water with calcium also retards or inhibits the hydration of clay. In addition, attapulgite clay is used to build viscosity in saltwater muds, but filtration control must be obtained by adding starch or cellulose. Finally, inert solids include barite, that is used to increase the weight or density of drilling mud. If workbooks are available, stop cassette and work exercise 2. Now let's get some general facts about water-based muds. Basically, there are two types of water-based muds: saltwater muds and freshwater muds. A saltwater mud is a mud whose water phase has one or more different kinds of salt dissolved in it. Some of the salts are sodium chloride, table salt, potassium chloride, calcium chloride, and seawater, which has many different salts in it. All saltwater muds are inhibitive. The water phase has some chemical in it that retards the swelling of any clays and shales that may be drilled. To lower water loss, a cellulose like CMC or a starch is added to saltwater muds. Cellulose or starches are used because bentonite does not hydrate very much in salt water. When high salt concentrations are present, a polyanionic cellulose is particularly useful. Chrome lignosulfonate, called spursine by this company, is a good chemical for reducing the viscosity of a saltwater mud. Corrosion may be a problem when using saltwater muds. You know what saltwater does to steel that is exposed to air. You can avoid this by adding an oxygen scavenger to the mud. Saltwater muds are good when drilling a salt formation. Since the mud is salty, it doesn't dissolve the salt formation, and near-gauge hole can be drilled. Saltwater muds are often used offshore. Since the rig is surrounded by a large amount of salty seawater, it is economical and convenient to use it as a makeup and treating water for mud. Now let's switch our talk to freshwater muds. Freshwater muds are broken down into three classes: those with little or no chemical treatment, those that are chemically treated but without calcium compounds, and those that are chemically treated with calcium compounds. About the only freshwater muds that aren't chemically treated are spud muds and natural muds. As it left, a spud mud may have bentonite or gel added, but that's about all. As at right, a natural mud is made by circulating only fresh water. The drilled formations add solids to the fresh water, and presto, you have a natural mud. As drilling progresses, a natural mud tends to get thick and viscous and have poor filtration properties. It has to be treated. A simple treatment is to add phosphate to the mud system. The phosphate thins the mud and keeps the viscosity down. However, phosphate doesn't do a good job as the temperature increases with depth. So, a different chemical may be used, like the lignite product the derrick man is feeding into the hopper on this rig. Lignite, lignosulfonate, and quebracho are good thinners for relatively high temperatures. But whatever chemical is used as a thinner, the old standby bentonite or gel is added to give filtration control. A problem with phosphate and lignosulfonate muds is that they get contaminated when cement, anhydrite, gyp, and salt are drilled. Also, drilled clay solids hydrate and cause problems, so an inhibitive mud may have to be used. Calcium-treated muds are inhibited muds. There are three calcium compounds used in calcium muds: calcium hydroxide, calcium sulfate, and calcium chloride. Calcium hydroxide mud is called lime mud. Calcium sulfate mud is called gyp mud. And calcium chloride mud is called, believe it or not, calcium chloride mud. Calcium muds have several advantages over other types of freshwater muds. Because they inhibit hydration, the calcium muds can have high mud weights with low viscosity and gel strength. Also, they can tolerate a fair amount of contamination from cement, salt, anhydrite, or drilled solids. The most serious problem with calcium mud is that it solidifies at high temperatures. This problem is most severe with lime mud, but both gyp and calcium chloride muds also solidify. To overcome the solidification problem, chrome lignosulfonate muds are used. The derrick man here is adding a lignosulfonate with the brand name of spursine. Lignosulfonate muds are inhibited muds that offer many advantages that calcium muds do not have. For example, lignosulfonate muds have greater tolerance for salt contamination, high temperatures, and calcium contamination. Also, they have the advantage of not needing organic filtration control agents for water loss control. True lignosulfonate muds contain several pounds per barrel of chrome lignosulfonate, say at least 10 pounds of lignosulfonate per barrel of mud. Because lignosulfonate muds are simple to make and easy to maintain, they are widely used. But lignosulfonate muds do have limitations. Mud stability decreases as the temperature increases, and above 400 degrees Fahrenheit, or 204 degrees Celsius, lignosulfonate degrades. Keeping desirable mud properties becomes a problem. Frequently, clear water, like the saturated salt water or brine in these pits, is used. Also, low solids muds are often employed. These are muds that contain less than 5% by volume solids. Clear water or low solids muds give relatively high rates of penetration. In other words, you can drill ahead faster. Since the water picks up solids during drilling, large settling pits where solids can drop out are necessary. Also, a chemical called a flocculant may have to be added. The flocculant causes the solids in the mud to flock together or flocculate and settle out due to their large size. Low solids muds are used when clear water alone can't keep the hole clear of solids or when filtration control is needed. Bentonite, adipolgite, polymers, and a viscosifier may be added in small amounts to maintain good properties. A fine screen shale shaker picks up solids from the mud as drilling progresses, and a desilter plus a desander remove more solids. The desander removes the largest of the solids missed by the shaker. The desilter removes even more of the smaller size particles. So, in summary, in this last section, we saw that there are two broad types of water-based muds: saltwater muds and freshwater muds. All saltwater muds are inhibitive. That is, they retard the hydration of clays and shales and are used to drill salt zones. Saltwater muds are thinned by adding lignosulfonate. Corrosion can be minimized by using an oxygen scavenger. Further, freshwater muds fall into three classes: those with little or no chemical treatment, those that are chemically treated without calcium compounds, and those that are treated with calcium compounds. Chemicals used to treat muds are phosphate, lignosulfonate, lignite, quebracho, bentonite, and calcium compounds. Finally, we mentioned clear water and low solids muds, and said that flocculants and large settling pits are used with clear water muds. With low solids muds, fine mesh shaker screens, desanders, and desilters are used to keep the solids content low. Regardless of the type of water-based mud in the pits, it should be selected to reach total depth safely at minimum cost, and it should be capable of maintaining both hole stability and mud stability as the bit penetrates the formations. If workbooks are available, work Exercise 3,